Hello, welcome everybody to today's webinar. We're going to cover the product update for autumn 2025. So this is showing you new features which have entered SimScale over the summer, so over the third quarter of the year. So to take us through those, I have with me John Wild, who's our VP of Product here at SimScale. Hi, John. Good morning.
Hey, morning. You all right?
Yes, I'm good, thanks. So yeah, just to remind everybody, please put your questions into the chat as we go along. We will be able to make sure that those go to the right expert in the company and we'll get an answer back to you, Amy. All right, so if we move on to the next slide, we're just going to briefly frame this new feature set with SimScale's mission. I think it's always helpful just to remind ourselves what the actual mission of the company and the product is. So SimScale, of course, always been about making simulation more accessible, more scalable, easier, faster, more seamless. And today, the way we describe it is that SimScale is empowering engineering teams everywhere to innovate faster by exploring thousands of engineering decisions in seconds. And that kind of idea is really what we're driving towards and what all of the new features should support. And whether that would be new technologies for accelerating processes, predictions, workflows with AI, or whether it's new physics to allow new analysis types, or just to make the user experience more seamless and consistent across all of the different parts of the product. So yeah, do you have anything to add, John, at this point?
I don't think so. I think that was pretty clear. Let me try and think. I mean, maybe the everywhere part is kind of important, and how easy it is to get your hands on SimScale. I mean, everything is in the browser, right? And there's no installation, no licenses to manage, and I think that helps us to enable the everybody part. I think that's really useful. So the fact that there's no install helps so much, and IT teams generally, once we've discussed security, obviously, which we can also discuss and prove and validate, are very happy that there's no installs to manage, right? So every time there's an update, there's nothing to think about anymore.
And I guess maybe it's also worth mentioning that if you're watching this and you've actually never used SimScale, never tried SimScale, you can actually go onto our website and open up a community account and try it out for yourself. And in fact, you can even go and look at an interactive demo without even signing in, so you can really easily see what this looks like.
I'm winging it now. I know we didn't agree to this, but we can, right? So you can really just go to simscale.com, start simulating now. You can create an account and then just start to experiment. So for any users at the beginning, it's free to experiment, and you get the results for the first 10 simulations.
Nice. Yeah, that's pretty unique. All right. So yeah, if we move on to the next slide, I think we've got a little agenda. So we're going to quickly cover how new features are released, and maybe also referring back to the cloud native aspect there. Then we'll run through the new capabilities. We're going to cover AI, CFD, FEA, and electromagnetics. And then we'll also cover general kind of updates and user experience updates towards the end. So yeah, talking about how we release new features. So how is SimScale different then from like a desktop application?
Yeah, I think the difference here, and it connects to what I said before about not needing an install and not needing to worry about updates. So I've used desktop CAD and simulation tools for, I don't know, decades, I can say now. And normally companies don't update when an update comes, right? Because you've got the true tried and tested software that you continue to run. SimScale works differently to that, and we have to do a lot of validation as a consequence. But what it means is that as soon as an update is ready, it could be a new AI option, it could be new controls in your dashboard, it could be a new solver, that will immediately be rolled out. So as soon as you log back into SimScale or refresh your browser, the new features will be there for you. We did that recently with plot over line, so the post-processing plot over line. It's really cool that users immediately they're asking for the feature and they just need to refresh it. It's there for them. It's kind of beautiful, I think. But it means that if the solver changes, it could change results. So it means we have to do lots of validation. So no changes are ever released until we've passed, until the new solver changes have passed through validation. And then every night we run a whole validation test suite. And then I think every week or every 2 weeks, we do a much larger validation test suite, just to make sure that everything's in hand. But I think the main thing really is that for me at least, it means that users can get new features as soon as they're ready.
Yeah. And then you can go and have a look at the roadmap page on our website where you can scroll back through new features over the previous quarters to see see whether you've missed anything. And you can also look at what's in development and what's even being considered.
Yeah, we try to keep this as up to date as possible. Sometimes it's a tiny bit lagging, like one feature you'll see here we're just about to talk about. It is released, but this just sometimes needs a bit of manual work. But you can look back over the last years and years at all of the different features that we've released. And if we focus on these, this is pretty much what we're going to talk about in this session, right? Everything that was released during the third quarter.
Lovely. Okay, so let's get into it then. So I think first we're going to talk about AI. So I think you've got a slide here just talking about what the overall AI offering is, because it's something that we're very excited about. Here at SimScale, we'll be talking about it a lot. So I think possibly our users are going to have heard lots of webinars covering AI recently and seen maybe social posts about it. So yeah, should we have a brief recap?
Yeah, sure. Strange because hardly anyone talks about AI these days, I think the recap is kind of important, I think, just to make sure that everyone understands what the difference between the different AI offerings that we have are. So we have engineering AI and physics AI. And I'll explain what those are in a second, but if we think about the whole design process, on the left-hand side, we've got a designer doing some designs, or an engineer doing some designs, anyone producing CAD models. And once they think they found or have produced the design that should meet the requirements, there's normally a simulation lead time. So that means the design is ready, it's marked as ready, and then it goes into a holding pattern and it is waiting until the simulation specialist has time to pick up that simulation, run with it, produce some results, and tell the designer if the design does meet requirements. So the simulation lead time is normally a waiting period as things are passed between different people. And then on the right-hand side, we have the simulation cycle time, where the simulation engineer, normally this is a bit shorter, but it's the time that they take to do the actual simulations. And then if we think about how engineering AI and physics AI fit into this, engineering AI is designed to fit into the left-hand side. So we want to shorten the simulation lead time. So for us, we don't think it's great if something's ready to be simulated and it's not being simulated. What's happening in that time? I know there's a long queue and people are waiting for work to be done, but if we can shorten that, all the better. And that's the goal here. So we want to empower anyone who's working upstream to use our AI, so either chat to the agent or use some automated workflows to do the simulations. So cut right straight to the simulation and not have to have that waiting period. So that's engineering AI. And so far we've got a workbench agent. We can talk about that in a bit. That's the first part of engineering AI that we've released. And then on the right-hand side, we've got physics AI. I think most people know what this is by now. There's lots of companies doing similar. Although, yeah, so maybe I'll explain it. There's lots of companies doing similar, but I think we're a bit different because, so physics AI is not running the simulations in a traditional way, but it's using AI to predict what the results would be. So yeah, lots of other companies can do that, but we have done it in a way where we've made the training very easy. So all of this can be done inside SimScale in a dashboard, and you can easily pull results from different projects and soon from third-party results as well, so from external tools. And then the AI can do some predictions for you. The cool thing now that makes us different is that the engineering AI can leverage physics AI. So if it's doing some design optimizations, it can use the physics AI to do the optimization really quickly. And because we've got now 12, 13 years of history of building the traditional solvers and the kind of tried and tested methodology for solving simulations. Once the physics AI says, okay, I've got my best result, we can always run a traditional solve just to validate that for ourselves.
So it's like that, having that side by side and being able to easily switch back and forth between the like traditional and the AI. That's really a unique feature.
I think so. Yeah, and it's
Yeah.
super easy to do. So any setup can be leveraged between physics AI or traditional solves. So there's nothing additional to do. You can just choose in the moment.
And it's nice to be able to actually view the results in the same environment as well, rather than needing to use kind of different tools to look at the outputs of those different things.
Yeah, exactly. And then thinking just about engineering AI, we have now a workbench agent that sits inside the platform and is there to sit alongside engineers and help them simulate. So if you've got questions along the way, like please check my setup for me, or do my boundary conditions make sense, or anything from general kind of simulation questions. So it can pull from the internet and our documentation, or it can do full setups. So you could say, I've run this before in a different project. Can you reuse that setup and apply it to this use case? So it could do lots of different things, from just general kind of Q&A to automatically setting up things for you and validating your setup as well. I think this is different to what everyone else is doing. I see a lot of agents that are really providing documentation. So it's kind of a nice way to talk to a Google search, kind of, right? But this is different, I think, because the AI or the LLM now is really integrated into the SimScale platform.
And I guess we're using the term agent, and that means that it can actually take actions on your behalf. So you can ask it to do things to your model setup and configure things for you, and even run simulations for you, right?
Yeah, exactly. So you could just say, use my standard test case for running these electronics cooling units, assuming it knows them and you've told it before, or you've given it the reference as to where to find that information, and it will just do everything for you. And again, I think it's amazing. It saves so much time. But the nice thing is it's all there to see. So there's nothing hidden. You can see the choices it's making. You can always check its setup. And again, you can use physics AI or traditional solves. So yeah, pretty exciting.
Yeah.
As well as the workbench agent, our customer success team also have an AI chat support. So we anyway have the ability to talk to one of our engineers, and normally they respond in something like a minute, maybe 2 minutes. So you can get expert help if you want it. If not, you can always just talk to the AI agent and get some help in fewer seconds. But if you want to talk to a person, you also can do. We've actually found that this is really, really helping. I'll be honest, I was a bit skeptical. I think maybe because I'm not looking at this project so much, but the response has been amazing from people who've used the agent so far. And it's really helping to solve problems without our support team having to get involved often, which is pretty impressive.
And I guess it can kind of fill the gap, especially if you're in a time zone which is far away from where your support team is as well. It can kind of answer questions in the middle of the night and that kind of thing if needed.
Yeah, that's true. What it can't do is interact. It's not the LLM that we built that's kind of like interacting with the SimScale platform, but it has access to the internet and it has access to all of our documentation, and we're giving it knowledge all the time.
And is it worth just mentioning the actual availability in the product, because this is available to everybody, and in fact this is also, I think, even available before you've logged in to SimScale.
Yep.
But the engineering AI agent is a bit more in development.
You could say it both ways. I mean, it's both in development and it's a bit more exclusive. And so it's currently in beta. Some of our customers now are testing it to really kind of, like pressure test it and put it through real workflows. So we think it works, but it's really good for our customers to test it and let us know. And yeah, if you are a customer and you want to test it, let us know, and we can probably line something up. But you're right that the Ray AI agent, which is really a support agent, is there for everybody. Yep.
Lovely. All right. So should we, let's go on to the physics analysis types, I guess. So we've just categorized them by CFD first, and then we'll look at structural and then electromagnetics. CFD, I think we've got a couple of nice new features here. So yeah, the first one, variable time steps in the multi-purpose analysis type.
Yeah, we've got really a lot of features to talk about actually, especially in structural. We probably have to speed up.
Yeah. Thinking
I apologize if anyone's watching. Just watch on 1.5 speed, and it should be good. I think within that hour. So yeah, the problem with that we can have with rotating machinery is that if you want to run something transiently, so capture like small iterations over a long period of time, the simulation itself can take a long time. There's just a lot of data to capture. With variable time steps now, what we can do is say, okay, run the pump, but run it every like maybe 1 or 2 or blade steps or 1 full revolution for a while, just to get the flow moving, get the stability looking good, and then kind of run a fine study with smaller changes and smaller movements to get the accuracy up. It just means that really we run much faster and more efficiently, so it's more cost effective.
Very nice. Yep. Sounds good. Yeah, and then another one here about CHT, so the immersed boundary method, CHT, being able to continue runs. And I guess this is a feature that is available for other analysis types. So it's about kind of consistency across the different analyses in SimScale.
Yeah, that's right. I mean, IBM is one of our newer solvers. So before everything was body fitted, this isn't. But it means now we can handle much more kind of gnarly or nasty geometry, like you can see on the top right. It's really complicated and organic, and the IBM solver can handle that. And yeah, you're right that before we couldn't continue a transient analysis. So you had to, if you wanted to run for 1,000 more, you had to start from the beginning, which is not great. It's not cost effective. So yeah, you're right. We're adding this feature to give feature parity across the different solver options.
Okay, and then this one, I feel like we need a little history lesson here to understand this one.
Yeah, I can do. So when I joined SimScale, it looked like this actually. No, it didn't look like this, but the list looked similar. So we had conjugate heat transfer, and it was frustrating to use. It took forever to converge. Actually, that might not be even an exaggeration. It was difficult to use, really. So one of the early decisions was, let's do better, and we built conjugate heat transfer V2, which is much more stable, much faster. It really converges, and it's more accurate. But like you saw with IBM, it takes time to add features to have feature parity. So it took a long time to have things like rotating regions, for example. And so we had conjugate heat transfer. I think it just said V1 or old, I can't remember, and then CHT V2, the new one. And now we've got to the point where we have feature parity, and we are like sunsetting the old version. And now conjugate heat transfer that we see here is the new version, and we will no longer use the old one. Was that a good explanation? Felt like it was like it got tangled like spaghetti for a little while.
No, I think it made sense. So yeah, and we just don't want people to be confused when they go to set up a new simulation and can't find V2. Yeah, that's the reason. It's the same thing, but we've just rationalized the naming.
Exactly. We'll keep doing more. So like in the end, convective heat transfer and conjugate heat transfer have now very similar capabilities, and we'll start to remove any that are superfluous. So we limit the amount of choices we give to our users.
Makes sense.
Small one. Periodic boundary conditions, not too complicated, right? But it's nice if you've got some kind of complicated model with a repeating pattern, and you don't want to simulate the whole thing. Now you don't need to. Again, this is really getting us to feature parity. But now we can just take a small section, apply periodic conditions, and we're up and running.
Very nice. So that concludes the CFD list, I think.
Mhm.
So now we're on to the very substantial FEA section. So this has got lots of new capabilities for the Marc solver, which we introduced in the early summer. And since it was first released, then the team have been busy enabling all sorts of cool new features, basically, for it, haven't they?
Yep, exactly. It's a good problem to have that we have lots to talk about. And yeah, you're right. I mean, now we have hexagons Marc on the platform. At the beginning, we only had a couple of boundary conditions, and obviously Marc is very capable. There's many more boundary conditions, many more material types, lots of different things to add. But we have to do it step by step because, like I said at the beginning, we put everything through this validation test suite. Everything has quite kind of stringent Q&A. So it takes a long time to just add a boundary condition because we want to do it properly. But yeah, now there's quite a lot from last quarter.
Right.
Starting with
I should get my stopwatch out. So yeah, load steps.
Yeah, so without load steps, we could only run how to explain. You could only have one thing happening at one time. So you could apply a load, like you can see, to this pipe being bent on the top right. It would just, you could have it bending once and it would kind of follow down and around the corner, but then you couldn't release the pressure at the top or the restriction at the top and then have the roller roll back because it runs in lots of different stages, and that wasn't possible before. Now with load steps, we can do that. So there's loads of different applications, like with rubber forming or being squished, and like this pipe forming as well. Lots of different applications that our customers are asking for, and now with load steps we can do this.
So it allows you to apply like a subsequent load to a deformed shape, I suppose.
Yeah,
like in this case.
Exactly.
Yeah. So
as part of
yeah,
the same simulation, though.
yeah.
Yes, exactly.
So maybe another good example is like if you've got a door seal, like a rubber door seal, and you want to fit it into a space which requires it to be deformed, and then you're going to like close a door onto it or something like that.
Yep.
So you need to do that in 2 steps.
Yeah, exactly. And you can have as many steps as you wanted. I've seen some that look unbelievably complex. But yeah, that's the engineering process, right? So it's
Yeah.
good you can capture it now. Contact forces. So inside SimScale, there's something called result controls, where we can take information back out without having to look at post-processing. We can grab numerical data, and things like this are important because we want to know if there's a contact that still exists between a couple of parts. So that could be if the contact force drops too much, we could have learned that a seal no longer works. Or for example, if there's an electrical contact, it's dropped enough that the current could no longer pass between 2 parts. So it's really important for us to like be able to look at the small details and make sure a contact is sufficient for things like that to still take place.
Makes sense.
Second order meshing, we have this already in other solvers, but it's important for us. If you look at the image at the top right, because Marc's very good at capturing large deformations, and first order meshing isn't so amazing here. Second order meshing is better because everything can deform kind of nicely. So now we have this enabled, we should be able to get more accurate results when we have much larger deformations like you can see here.
Very nice.
Table stakes, I would say, automatic contact detection, but this didn't exist in Marc before, and now it does. No, I'll correct myself. It didn't exist in Marc on SimScale before. It definitely existed in Hexagon's Marc, but we didn't have this in SimScale with just this solver. Now we do. So now you don't need to set up contacts manually anymore. The model will automatically detect everything for you, and then you can also still change contacts if you want to, but the automated part obviously does a lot for you. It gains you a lot, and it automatically glues everything for you.
So you've just got to go through and select if it's a different type of contact that you want on a particular pair.
Yeah, exactly. Like this one, So you could say, okay, this contact, it was found in automatic contacts, it was glued, but we've got a non-conformal mesh, so the mesh is different on the two parts. The nodes aren't shared between the two parts. So I want to change the tolerance just to broaden it out a bit, and it will make sure then that those two parts have still a glued tolerance. So it could find this contact with automatic contact detection, but if when you run it, it doesn't perform quite as you expect, it might be that you have these gaps forming, and then you can go in and you can change individual contacts.
Got it. I see. So you can see in the top left picture that there's a small gap opened up there between the kind of the rubber part and the steel part, or something in the middle, right?
Exactly. And then once it's glued on the right, you can see that they stay glued, which is what you intended in the first place. You might have intended in the first place. And now also Marc has lots of capabilities with different material types. So the Marlow material is good because now we don't have to type in different values to try and match test data, but we can now use a function instead. So we can get a step towards having more accurately modeling material data, so matching to test data. And now we can start to model things like you can see in the bottom right. So a really kind of complicated material behavior. But yeah, now we can describe it, we can simulate it.
That's an insane looking simulation in that animation.
Different to the door seal, right?
Yeah. Indeed.
And then I guess this gets a little bit more complicated too. So we can now model viscoplastic materials. So these can change, the material properties can change depending on what happens over time. So if you look at the stress strain graph at the bottom, what's happening is that the material is breaking down over time, and we can start to then model creep, and we can model damage as cyclical loading takes place.
Very cool.
Yeah, I think so. It opens up lots of different possibilities,
Yeah.
So we're doing a lot of this for customers who need this, really. I don't think many customers will use this because it's pretty advanced, I would say. But those that do have huge benefit from it already.
Yeah.
New boundary conditions, so remote displacement. So here in the bottom right, we're picking a couple of faces, and we're saying that these are going to be connected to a point in the middle. So we've kind of put like beam connections between the two, so it's rigid. So that face has to stay fixed, and then afterwards we can rotate the center, and everything will rotate as one. So there's a couple of different steps. So first connecting everything, and then adding this rotation.
It seems like it's like a very powerful, like generalized way to apply any kind of motion or rotation or force or anything like that, right?
Yeah. It's, I mean, the nice thing here is it means that nothing will kind of slip around or fall apart. We don't have to think about contacts in that way. Yeah, it just gives you more possibilities to set things up in different ways.
Yeah.
In probably more representative ways. And then symmetry, again, my point of view, this is table stakes. You should always model symmetry if you can. And now we can as well in Marc. It works a bit differently to other softwares or other solvers, where if you look at the image in the bottom right, you use a cut plane. So instead of choosing symmetry surfaces, you have a plane, which does mean that parts, if you have it set up, hang on, how to explain? Those parts won't pass the symmetry plane, but you could have a part that does pass the symmetry plane later. But these ones that are currently in contact won't do. So it actually means that you can do much more with symmetry than having to assign it to just surfaces.
I see, yeah. There we go. That was all of the FEA new features. Yeah, I think we got through those in very good time, actually, in the end.
Good.
Yeah, so we have, I think, a couple to mention for electromagnetics, don't we? Yeah, so the one that you saw in the roadmap at the start, the Litz coil, I think, is the first one. So yeah, I was looking up what a Litz wire is, I have to confess. And it seemed to make sense, like all about trying to avoid losses in skin effect for high frequency.
Mm-hmm.
But I couldn't quite understand what I'm actually looking at in the picture there.
Yeah, so I guess inside each of these coils, inside one pipe, essentially, like the yellow, right, would be lots of bundles of electrical wire. So lots of them all together. Each one would contain lots of different wires as well, and then there would be insulation between each one. So loads of different circles, all within one single cable or wire. And that's hard. It's possible to simulate, but you don't really want to simulate all of that complexity. The same like with a heat pipe, you don't want to simulate the phase change that happens inside a heat pipe. It doesn't make sense if you don't need to, and if you can just have a material that that will just simulate it close enough without having to simulate all of the physics. And that's what this Litz wire is doing. So you can tell it, you can tell SimScale what is inside the wire, and then SimScale will simulate the effect of that in the global scheme of things.
I see. Okay. So you're not so much not so much interested in what's happening inside the bundle of wires, but what they're actually doing to something else.
Yeah, normally. Yeah, I mean, if you want to know what happens inside the wire, then you have to model the details, right? But you normally don't want to do all of that. And the other EM feature is to do with transient simulations. So like we said before with rotating machinery, transient simulations can take a long time if you're running lots of different time steps. With rotating machinery, what we said is that we want to have coarse time steps at the beginning and fine time steps at the end. This works a bit differently because if we know that there's a periodic, something changing periodically inside the simulation, we can tell SimScale that we know that, and then it will account for that in the simulation. So it's kind of running a pseudo transient simulation to not run everything just transiently with tiny time steps, so it can run it in a much shorter time. So it's really a kind of cost efficiency feature, really, and time actually, and time. But it isn't compromising on accuracy in any way.
Yeah. Very nice. Right. So that's all of the the physics specific capabilities that we were going to cover. And then we've got a few here at the end that are kind of, I guess it's like the everything else category. So there's a bit of pre-processing, a bit of meshing, a bit of post-processing in there. So yeah, let's take a look. I'll
tell the my pre and post-processing product manager that she's actually just doing everything else. And then I'll give her your address. We'll see what happens. No, I think these are, I mean, these are essentially non-physics based features, right?
Yeah.
But anything that helps with CAD cleanup, simulation preparation, like efficient post-processing, so getting results back, all of that.
Very important non-physics.
Now.
Yeah, but they are, and this one is really cool. I really like this one. I think everyone really likes this one, right, Tony? Because this is something that I remember struggling to do in other tools. Struggling to do this in a nice way, rather than just kind of clipping a visualization, but actually showing it in a nice way like this, that you could actually like put in a report even, or
yeah, I find it super useful. I mean, for me, is just the fundamental of I'm doing some geometry changes and I want to see inside the geometry, so I can do that really quickly. Then I can make the changes that I want to. I mean, as for simulation tools, this doesn't always exist, but in CAD tools it always exists, right? And we're kind of in a little bit in between now. So we have the simulation tool, but now we're giving SimScale so many CAD capabilities, we need this kind of functionality as well.
Yep, very nice.
And this, yeah, I mean, like I said, we've got lots of different CAD functionality now. You can see the options along the top. Until recently, if operation, so some kind of feature that you've added was taking a long time, you couldn't stop it. Now you can. So this seems like a really small thing. It is essentially, I would call it almost product debt, right? It's like a no-brainer. Why did we have it in any other way at the beginning? Because it was really hard to do it this way. yeah, the users who've experienced waiting will appreciate this, I'm sure. And then within meshing, we have automatic extrusion detection. So if you're modeling a long pipe, generally you don't want, you don't need to spend time, or the mesh, you don't need to waste mesh on like the normal kind of randomized mesh or inside a pipe. It's not very efficient. It's also probably less accurate if the flow is totally linear. What you can do is say, okay, I've got an extrusion here, just extrude the mesh through that pipe. But now within SimScale as well, you can automatically do that. So it will search the model for you, and it will figure out where extruded meshes can exist, and then it will apply them for you. If it's got it wrong, you can change the options here from shortest to longest in case the direction goes through a pipe from the outside surface to another outside surface, which isn't good. You can change the longest and it will extrude along the length. So the chance of needing to change this, I think, is probably small, but it's there in case the extruded mesher gets it wrong. But it's a super nice automation, honestly. I've never seen it really automated in the nice way that we have. It's really cool. Massive time saver.
Very nice.
Any questions, Alex?
I suppose I was looking at that model and wondering where in the pump it would actually be creating an extruded mesh.
I mean, it's a good question.
But I guess it'd be maybe like the outlet that you see at the top.
Yeah, I mean, what you really want to do here is
be...
extend the inlet and the outlet so that well, there's two different ways. If you extend the inlet, you should have nicely developed flow before the flow reaches the pump. Or if you had a velocity there, you could use a fully developed flow inlet, right? One of the two. I'm just trying to think which way around it goes. Normally you don't do that though, because you have the flow being pulled out, so you have a pressure on the inlet, because you want to know the pressure gain at the outlet. So the pressure outlet is normally higher. So you normally you can't assign a flow rate at the inlet. You normally have to have a pressure, which means you need a long tube or long pipe for the flow to be fully developed. Then you want to extrude the mesh in that pipe. So really what this image should show are two pipes coming from the inlet and the outlet. That would be perfect. Then it would make the discussion much easier.
Sure.
And the last one, this is for AEC really. So our pedestrian wind comfort analysis type. It's very application specific. Before, we couldn't add cut planes inside the post processor. So you were kind of restricted to just what you could see. Now we can add cut planes and we can start to investigate inside the model as well. So obviously we could do this, we could do this for all other analysis types anyway, but we couldn't with wind comfort because it uses a very specific type of solver, a lattice Boltzmann method. Now we can.
Yeah, I'm looking forward to using this one. I think it's going to be useful.
Cool.
Cool. Great. Well, thank you very much, John, for taking us through those.
Good.
Looks like, yeah, a really solid set of features there, especially for the structural mechanics enthusiasts. So, yeah, as I mentioned, you can drop your questions into the chat. And obviously, this is a pre-recorded webinar, but we will pass those questions on to our experts in the company and get those answers back to you as soon as we can. Otherwise, thank you very much for joining today, and we'll be back in the new year with our winter update, I guess, won't we, John? Yep,
very well. One quick question. I guess this also will go on YouTube, so if you've got questions, you can also post them there, and I'll check in and answer.
Awesome.
Cool.
All right. Thanks very much.
Thanks very much. See you next time.
Bye, everybody.